I hit the record button, so we're in good shape for that. Oh, wow. Bear with me here. I got to draw one real quick diagram because I just kind of botched this one that I was drawing. Again, sorry for the delay. I can fold that. Okay, there we go. Better. And we have this. And okay, I don't see anybody else here, so I'll get started. Get this. Okay. So, to be honest with you, I was not very happy at all with the last Zoom meeting we did with my performance in that. It wasn't a good lecture. Uh, I don't think there were inaccuracies in it, but it just wasn't presented very well. And what I really need to do is just introduce people to this idea of inverse trig functions. And so this is another attempt at that this morning, but it's going to be short. I just want to give you the general idea of these inverse trig functions, of what is going on with them, and why we would even concern ourselves with them. And sometimes the notation with these can really be confusing. And so I want to try to just give people just a real solid, simple understanding of what these inverse trig functions are. And that I think that'll make things much easier for you when you're looking at problems, perhaps in a future class or in some work setting. You may actually have to do some calculations, things of that nature. So, an inverse trig function, and what let me see, I'm going to see if I can enlarge this screen here. Okay, and remove this around. So hopefully you can see that pretty good. If I put my hand there, I think it focuses it better. And then it changes again. Anyway, I think you can see that. So the general idea with an inverse trig function, okay, let's stop a minute and just think about mathematics in general and an inverse function. Okay, so what's going on in math when you have an inverse function? You can think of that as reversing the process that a function performs. Okay, and so here we have so in trig we've got 6 circular functions, 6 basic functions, right? Sine, cosine, tangent, cotangent, secant, cosecant, and cotangent. All right. Now, in math, in general, for any function, in order for that function to have an inverse, the function has to be 1-to-1. And so what does that mean? That means if I have, let me get another paper here. Okay, so 1-to-1. Okay, so if I have some f of x equals y, so I have a function that is a function of x, and the value of that function, if I insert x as an independent or input variable, I produce y as a dependent variable or output variable. So 1-to-1 means that you can think of it this way. You could have 2 spaces here, okay? And over here, we have points, and this would be the x space, if you will. And this is a y space, okay? And we have points over here. So this notion of 1-to-1 has to do with this map. So this function, f of x, takes an x value and it produces a y value, okay? That's what the function does. So for this function to be 1-to-1, any x that you select over here in the domain, this would be the domain of f of x, right? This space over here, and this space would be the range. So any x point that you select in the domain can have only one y value in the range. Okay, that's a requirement of a 1-to-1 function. And also, there's another requirement. And but first of all, so with this first requirement, so if this x produces this y, okay, it can't also produce some other y. For this same value of x, you can't have another value of y. You can only have this one value, all right? But the same can be said for the opposite direction. For any y you select in this space, there is only one x. That corresponds with that y value, okay? So if I have a y value over here, there cannot be more than one x value in the domain that produce this same value of y. Okay, so that is what we mean by 1-to-1. For any x I select, there can only be one y value, And the reverse of that is also true. For any y that I select in the range of this function, there is only one x value for that y that produces that y, okay? And so if a function has this property, so if f of x, and technically in math, the name of this function would just be f, okay? This technically is a value, but if this function f, or f of x, is 1-to-1, okay, then f of x has an inverse function, all right, okay? Okay, because so let's look at a trig function here. Let's look at cosine of x, all right? So we'll make this axis x, this axis y, and we'll draw a basic cosine function here, right? And it goes on, and then this goes on, you know, in the opposite direction forever, right? Dot, 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 dot. This is a cosine function, okay? So here we would say f of x equals cosine of x, okay? And f of x is y. That's the y value. So you give me an x value, and I didn't draw this. This doesn't look great here because, well, yeah, I guess it's not too bad. Okay, so, and this is one of the things that makes all of this really confusing, is the fact that, okay, here, what is x? X is it's a real number that is the measure of an angle, okay? And this is why this stuff gets really confusing, because of the notation, all right? Because a lot of times we're talking about, like, if you talk about the x, if you're talking about the unit circle, x is not an angle anymore. X is just a coordinate, right? X is a distance value on the x-axis, but x is not the angle. Well, when we plot a function this way and call it f of x, x here is an angle. So x, and whenever I talk about angles, I like to call them theta, okay? So we could have written here f of theta equals cosine of theta. I personally like that better. They don't do that much in this book that we're using at all, and there's reasons they don't, okay? But it's I think this is a good notation. It helps you to make sense of things a lot of times with this variable notation. But remember, anytime we have a trig function, there's one of the circular functions, be it sine, cosine, secant, whatever, and you'll have a parentheses, and then you'll have a value inside the parentheses. So the value inside the parentheses is always, for a trig function, it's an angle, okay? Now, we represent that angle with a real number oftentimes. And that's why this notation gets confusing, because let's see, sometimes you'll see f of t is cosine of t, and you'll see f of x is cosine of x, and you'll see, well, you don't see this much, but in some of the books I've looked at in the past, and there's certainly nothing wrong with this, okay? But you can write, and I prefer this because I immediately know I'm talking about an angle. Here, when I see this function, because it's a cosine function, I know this thing is an angle. But if I'm working with it later and I just have this x by itself, I may not realize that it's an angle, okay? T, okay, so x is a real number that is also the measure of an angle, okay? And t is the same thing. T is a real number that is a measure of an angle. And theta, we list as a number, as and I guess you could say real number, but a number, you label it with a number, which is an angle, okay? And so what makes all this confusing is when you have the unit circle, you have x and y. So this x is not an angle, okay? This x is just a coordinate. This x is just a real number. So this x value on here is just a real number. It's the coordinate. It's the x coordinate, okay? And it represents a distance from 0. So when you have a value of x, that does represent a distance from 0, okay? But it's not an angle. And then you have a ray out here with some terminal point on this unit circle. And so here's an angle, we'll call it theta, okay? And when we do this, and we went through this before, earlier in class, but if we measure theta in radians, then this distance here of this arc length, that is, this is also a measure of an angle, okay? And that's why I kind of like t. I like t better than I like x when you have these expressions, because oftentimes you'll represent this arc length, or a directed arc, okay, an oriented arc they call it, which is a segment of the circle, but oriented meaning it has a direction. So it started at some 0 point, it has a direction to it. But an oriented arc, T is the arc length, okay? But if theta is measured in radians, the value of T is the same thing as the value of theta. So T can represent theta. The number that T is the same number that is the measure of theta, okay? So I like this notation pretty well. And even that can get a little confusing because sometimes in these equations, T will represent time, okay? And when you have, it's kind of a different thing, but you have theta equals omega T, right? So here, F of theta would be F of omega T, not F of T, right? And so in this case, T does not represent the angle, but T is, oh, you can't see that, I'm sorry. Okay, so T is an arc length. It's this arc length. And if theta is in radians, the value of T, this distance measure of this oriented arc, is the same number as the measure of the angle in radians. So we can just talk about theta by talking about T. It's the same number. If I say T is 1, then theta is 1 radian. If T is 2, theta is 2 radians. So here, when you just have F of T or cosine of T, T is an angle, okay? But you can also represent an angle as omega T. And omega is called the angular frequency, we learned, right? But here, the angle is omega T. It's not T. It's these two multiplied together. So all this notation always depends on context, because here, T could be time, okay? So theta is proportional to T. If you double the time, you've doubled your angle. But T is not the angle. The angle is T times omega, which is the radians per unit time times the value of time, T. That gives you the angle. So it always depends on context, what things mean. Here, this T is an angle. Here, this T is not an angle. It's either, it could be a time or it could just be a distance. It could be a length. But the angle is actually this T value, whether it's time or whether it's a distance, times omega. So context is always important. And the one thing that's solid here that's easy to know is anytime you have a trig function, whether it's cosine, sine, tangent, whatever it is, when you have parentheses, I like to think of whatever's inside that argument, and that's called the argument, whatever's inside the parentheses is always an angle. The whole thing's an angle, okay? So T is an angle here, theta is an angle, here X is an angle. Over here on the unit circle, X is not an angle. X is just a coordinate. X is the value on this axis. But if it's written this way, this X is the real number that represents this angle. So X would actually be the same thing as T here, okay? So I don't like writing this way for that reason. But in calculus, you'll see this a lot. You'll see all kinds of trig functions of X, cosine of X, sine squared of X, tangent squared of X. But whenever you have a trig function, whatever's in the parentheses is the angle. So when we had things like we were graphing before that were a little more complicated, if you had a function like cosine of 2t plus pi over 3, okay? So here we know this whole thing is the angle. So you could write this as cosine of theta, right? Or you could say f of theta. This is a function of theta equals cosine of theta. And then when we made our graphs, we were actually graphing. Okay, if we graph this, we're not graphing theta and cosine of theta. We're graphing t and cosine of theta, because this is y, right? Y is f of theta. Y equals this. So this is an f of t. And that's a little confusing also, actually. But yeah, this function of t is represented by cosine of this expression. And this total expression here would be the angle, because it's the argument of the cosine function. So in this case, this t is an angle because it's the only thing that in the argument of cosine. So t is an angle. Here, this t is not an angle. T is a variable. It's a real number in this expression, but t is not an angle. This whole thing is the angle. That makes sense. Okay, I like that. I'm happy with that. Anyway, that's what makes some of this a little confusing, especially when you start getting into the inverse trig functions, because you start confusing, well, you're talking about x, so then you start thinking, well, am I talking about something on this axis? Well, if you're talking about the unit circle, this is just a coordinate. So this is a real number that represents a distance, the x value. But if you have it inside the argument of a trig function, it's an angle. This is the same thing as theta. Okay. I just wanted to clear that up. So getting back to this one-to-one business here, let me see. Where do I want to go? Okay. So we've got this one-to-one mapping. All right, is there? Okay. If f of x is a one-to-one function, okay, then that means for each x, there's only one y value permitted, and it has to have a y value. And also, for any y you select, there can only be one x, because there are expressions where you would have, say, more than one, or maybe you would only have one y for this x, but maybe there's another x that gives you the same y, okay? So we could only have one y for any x we pick here, and we're not done yet, right? Because it's still possible that there could be another x that gave us the same y. And we have to take care of it in both directions. For any x, there's only one y. For any y, there's only one x. When that's satisfied, then the inverse of that function exists. There is an inverse for that function, okay? So let's look at one of our ordinary trig functions, cosine of theta. And here, and the book likes to use x here. So I'm going to use x. F of x is cosine of x. So since x is inside this argument, we know x is an angle, okay? So even though this looks like the coordinate axis for a unit circle, in both cases, x is a real number, but in this case, this real number is an angle because it's inside the argument for a trig function. So we know these are real numbers, but they also represent angles, okay? So if we look at cosine x, the problem we got, if we want to talk about, and remember the topic today is inverses of trig functions. So if this thing has an inverse, we've just shown up here that it has to be a one-to-one function. For any x, there's only one y, and for any y, there's only one x. Well, so let's pick a value here. Let's pick this value. Okay, here's an x value. So I plug this x value into this equation, and it gives me what the y value is. So I plug x into cosine of x, and I calculate that with my calculator, or I do a Pythagorean function or whatever, but I get the value of this. When I get the value of this, it's y. So for this x, which we know is an angle, it has some y value. So for this function to be 1-to-1, there can only be one x that has this y value. But here's the problem, which you see there, right? We come across, what? Here's another y value that's the same thing, but I'll call this x2. Now we've got a different x that has the same y, and you do the same thing in the other direction, right? So it's not unique. There are more than one x value that give you the same y value. So in order for us to have inverses and be able to use them, we have to put constraints on the function to make sure it actually exists and it meets this 1-to-1 requirement. So what's the restraint that we put on it? We restrict its range, okay? So for the cosine function, this is the point 0, 0 here, the origin, right? And this point here where it crosses is pi over 2. And this point here is pi radians, okay? So this is pi over 2 radians at that point. But we notice here, what are the values for cosine of x between 0 radians and pi radians? Well, they go from, this is +1, and this down here is -1. But what we see here is we've covered all the possible values. So the cosine of x always has a value somewhere between -1 and 1. No matter where we are, it always has one of these values on this line somewhere, right? So if we restrict the range of x, which is the domain of this function, f of x, so we're restricting the domain of f of x to put domain would be 0 to pi. So that's x can be equal to 0 or anything up to and including pi. Since we have a square bracket, these endpoints are included. X can be 0, x can be pi. It can be any value in between there, okay? But now we've got a function that is 1-to-1, because if I pick any value on here, there's any y value I want, there's only one x value that gives me that y value, okay? And vice versa. If I pick any x here, and I say, well, what's the y value for this x? Well, here it is, okay? Well, is there another y value for this same x? No, that's the only y value for that x. So it works in that direction. And again, if I pick a y, let me pick this y value right here, okay? I'll pick this y value, and I say, what is x for that? And I come down here and I say, okay, here's the x for this y value. Does this value of y have any other value of x other than this? And you look, and no, it doesn't, because it has to be on this line, right? So any y I select on here can only have one x value, and any x I select in this range can only have one y value. So this function is 1-to-1. Because it's 1-to-1, we're now allowed to have an inverse function for this cosine of x. And here x is the angle theta. So we could have written theta out here, and f of theta equals cosine theta. Or you could have written t, f of t equals cosine t. But in whatever you're calling it, you were restricting that angle, whether it's x, t, theta, whatever you want to call it, that angle has to be restricted to the range from 0 up to including pi. Okay, now we're allowed to have an inverse. We have a legitimate inverse. It exists. Okay, so there's the, there it is, restricted domain of cosine of x is 0 to pi. Okay, that's this region here. Okay, we got that. All right, now we can talk about some of this notation. All this will make sense. And this hopefully will help you visualize these inverse trig functions a little easier. Okay, so because of the requirement for a function to have an inverse, we restrict the domains of all the circular functions. So we do this for all 6 functions, right? For the cosine function, this is the domain it has to be restricted to cover all the possible value, to get all the y values that a cosine can take on, which is from -1 to +1. We restrict the domain so those numbers only occur once. We restrict the domain of the function. That is, we restrict the argument, the angle, to these values. The angle has to be between 0 and pi. Okay. And here's the big idea with the inverse trig function. Okay. So in a function, we start out. You can think of this as a space, right? We start out. We have angle space, and again, we could represent this angle. Here I'm calling it theta. We could call it, this could be t, it could be x, it could be omega t, whatever the angle is, okay? But we have an angle. We have a circular, one of the 6 circular functions here, cosine. Okay, so we have cosine of theta. And so this is the f of theta. F of theta is cosine theta. Okay, so what do we do with this function? We have an independent variable, which is theta. So we go over here and we say, what angle do we have? Oh, we've got this particular angle. We put this angle into the function, and then we operate on it with that function. We take the cosine of that angle. That gives us a real number value. And here we're calling this x. So x is just purely a real number here, okay? And it's the output of this cosine function. So we go from this space, angle space, we get a particular angle, we put it into the function, we output the value of the function, which is a number that comes from this other space. And this is called the image space of the function over here, okay? This is the image space of a function. So this is a map from theta space to x space. You can think of it that way, right? Cosine theta, all the values of cosine theta are some value of x. So that's what this trig function is, okay? So what's the inverse of that? Okay, an inverse is just like your intuition would lead you to think. It's like the reverse of that process, okay? So in an inverse process, we would start out with something here and end up over here. So the function's taking us from the domain, this is the domain, right, to the range. That's what the function does. The inverse function will get a value from the range of the original function, and it will output a value from the domain of the original function. So let's look at the inverse function. So for cosine, it's called arccosine. That's the inverse function of the cosine function. That's the name of it. And sometimes that's written cosine -1 of x. Okay, there are some problems with this notation, which I'll mention here for a minute. But I much prefer this arccosine notation. It's harder to make a mistake if you think of it and write it this way. And so what's this inverse function? Well, notice what's in the argument of this function now is x. And this is why I went through all that business about context before, okay? Because all that talk earlier where we had f of theta, f of t, and we even had f of x. Well, in that case, x was an angle, okay? When we had f of x, x represented an angle, just like f of t, where t is a real number. It's that oriented arc length that has the same value as an angle. And when we say cosine of x, if we say cosine of x is an angle, okay, because it's in the argument of a cosine function. Here, this is in the argument of an arcsine function. So x is not an angle here, not at all. What x is, it's just the real number. It's from this range space of the original function. So here, x is, you can't see that. X is not an angle. X is a pure real number. It does represent a distance from the origin on the x coordinate axis. But here, it kind of looks like, because you see this part of it, and you say, well, that kind of looks like our cosine function there, and we have this argument. But always remind yourself, once you have an arc in front of this, it changes the nature of what's inside this argument. This is no longer an angle. When you have an arc cosine function, this is a real number here, okay, which would be a distance, or it's a point on the x coordinate space, but it is not an angle. Now, the output of the function, okay, this function arc cosine operates on this real number x, and it produces an angle. And so what we've done here, this is the inverse process that is the inverse of the cosine of theta, okay? And up here I use theta on purpose, and x over here is the output, because here it's easy to see x is not an angle. X is a number. It's in the real number space. It does not represent an angle. And so I like to think about these when I'm just thinking about angles and inverse functions, inverse trig functions. I like to think of the angle as theta. Whatever it is, it's theta. Then because I know when I look at this symbol, I know that's always an angle. I don't have to think, well, is it an angle this time, but now it's just a coordinate over on this other plane, but it's not really an angle, it's a real number. I don't think of it that way. So if you think in your mind theta for the angle, that'll keep this very clear for you. Because down here, and that helps when you get to this stage, because here you know this is an angle, it's theta. Theta is always an angle. And this, even though it looks from this cosine part, it kind of looks like, oh, that kind of looks like arc and then cosine of x. So there's a temptation to get confused there and mix up the nature of what this thing is inside the parentheses here. And what this thing is inside the parentheses is just a real number x, okay? A number on the x coordinate axis. And so you could think of this as coming from the range of the cosine function, or this is from the output of a cosine function, okay? But this is not arc of the cosine of x. This, okay, this is is one single thing. Arccosine. It's not arc of the cosine of x. It's the arccosine. It's a single operation, and that stands for the inverse process of this, okay? So if we want to do the inverse of this, we have to take its output as our input to the inverse function. So this is a real number, goes into the arccosine function, and it produces an angle, theta. So very simply, the ordinary function takes an angle. You give me an angle theta, and I'll map it into I'll map this angle into this function value in real number space, okay? We'll obtain the value of this function given the angle as an input. We'll get the value of this function, which is over here in this range, in this image space. And if I want to do the inverse of this operation, I have to start with a number in this image space, in this range of this original function. This will be my input if I'm doing the inverse operation. So here it's the input. It goes in the argument, and it tells this function what value to go get based on this input, okay? So we're just reversing that process. And you could write this arc cosine x as g of x. So you could just give it this different name, right? And if you do that, g of x technically is a value. It's the value that you obtain when you plug x into this function. So g of x is this value theta for this value of x, right? But the name of this function is just g. So g it's written equals f to the -1, which means f inverse. So g, arc cosine of x, is the inverse function, f to the -1 of f of x, okay? F of theta, I should say theta here. Okay, so we see an inverse trig function takes a real number input and produces an angle as an output. So it's the reverse process of what a trig function does. So we've restricted the range of cosine of x here. And this, remember, this would be cosine of theta because this is a cosine function, so this is an angle. So theta is going from 0 to pi. And if we input, and the value of cosine of theta is the range of cosine. I'm going to put theta equals -1 to 1, okay? So if we input something from this range into the arc cosine, we're going to plug a value in here for x. It's between -1 and +1, and it's going to give us the angle theta that belongs to that. And once we have that, we would see the same thing in the opposite direction. We take that angle and we take the cosine of it, and we'll get x, which was this input value here. So yeah. So if you take I'm not going to write that. That would be confusing. Anyway, questions about that? The main point is always look at your function. If it's a regular trig function, you know this is an angle, whether it says x, t, theta, or wt plus pi over 2. That whole thing is an angle. And think of it as theta if it's a regular trig function. If you see arc and cosine or arcsine or arcsecant. No, this is not the arc of the secant of that. This whole thing is one function. It's the arccosine, okay? And when you have an inverse function, this argument, even though it looks a lot like this did up there, this is not an angle anymore. This is a real number. And this thing, the output of this, produces an angle. Okay, and there was another point I wanted to make. Oh yeah, on the notation. So much of this is just not tripping up in the notation, but and the book talks about this, right? So arc cosine theta. You could write that same thing. Okay, this is another way of writing arc cosine of theta. It means the same thing. And some books and some places use this notation. So you should understand that that is used. Our textbook does not like this, because, and there are reasons people can make mistakes. You know, in ordinary math, if I take a number, say 3 to the -1 power, what does that mean? In regular math, that means 1 divided by 3. This is the inverse of 3, which means the reciprocal. So it's 1 over that. This thing is not equal to 1 over cosine theta. Okay? So you could see this -1 and maybe think they're doing this. They're taking -1 to this thing, which is a cosine. But this is not a reciprocal. This is the arcsine. So this thing, again, produces actually, yeah, that's, I made the mistake myself. This would not be theta. I'll put X here. I just made the mistake that I've been telling you for a half hour, don't make. The argument of an inverse trig function is not an angle, okay? It produces an angle there. So X. So we write that same thing without the mistake in it. Arc cosine of X. They use this notation sometimes, okay? And it does not mean 1 over the cosine of X. It means it produces theta. So theta equals arc cosine of X, equals arc cosine of X. And the reason, another reason, the reason this mistake would be made is because when you write cosine squared theta, that's the same thing as cosine theta cosine theta, right? So you would read that as, well, it's the cosine, it's the second power of the cosine function. It's cosine squared, cosine times cosine, right? So that's why you would be tempted to say, well, this is the cosine to the -1 power. And we just said a number, you know, to the -1 power, 4 to the -1 equals 1 over 4. So you'd be tempted to do this. But you can't do that because that's not what that is. That's another reason I like arc cosine instead of cosine to the -1. And then the last point is I prefer T to X in a lot of cases. But I guess here X is better because it's just a real number and it's not an angle. If you're talking about You're just talking about the regular function, sine, cosine, tangent. I prefer t rather than x because t is that arc length, you know, for an angle. This is t is the length of this segment, and that's equal to this angle, theta. If you're talking about straight up functions, cosine t. So again, if you're talking about inverse functions, I guess x would be preferable. Then you're more apt to realize this is just a real number, doesn't represent an angle at all in any way. Okay, that's the end of that topic. I think this is the main picture to understand here, that you're just going in the reverse direction with the inverse trig function. And you have to restrict the domain to where the function is 1-to-1. So each circular function has its own restricted domain, okay? So you should probably look that up just for a good measure, right? See what the domain of the sine function, the domain of what you have to restrict the domain to for each of the 6 functions. And if you restrict their domains, you have an inverse function for them. Okay, I sent you the email about the final. And again, so if you've done all the homework since after spring break occurred, the final's optional. I'll get your grades to you Sunday of what your grade will be. You know, if you don't take the final Sunday evening, it'll be on there. This is what your grade is if you don't take the final, and then the final's optional if you have done all the homework since the midterm. And it's optional, so you can take it if you want to try to improve your grade. If you score higher on the final than you scored on the midterm, I'll replace your midterm grade with the final grade. So it'll effectively count twice, okay? It'll be double weight and your midterm will be wiped out if you did take the final and you scored higher. But you may already have a good enough grade. Maybe I haven't looked at them and tabulated all the extra credit yet. But if you've already got an A, obviously there's no reason to take the final. Or if you've already got a B and you're happy with that, you don't have to take the final, but you can. And then if you do really well on it, you know, you could possibly improve it. And I'll try to get that to you Sunday of what grade you currently have. Do I have any other questions from anybody? What number is y equals 0? From Alexis to everyone. It's in a graph where it talks about. Oh, okay. So Tucker straightened you out on that, Alexis. I see. That's good. Okay. You guys got any questions for me right now? Alexis is good. Tucker, you all right? Okay, good deal. You guys have a great weekend, and I'll work on grades this weekend and get them tabulated. I'll get you an email Sunday evening. Here's what you got. And by then I should be able, if you want to take the final, I'll be able to tell you which day it is. I've been trying to schedule that. I've ran into some snags on it, but I'll know Sunday. I should know Sunday what day the final will be. And thanks for all the tuning in, you guys dialing into these 8 o'clock meetings and following this. I appreciate it. As you could probably tell, I'm kind of learning myself. I had trig like 40 years ago, literally. I had a different job for decades, and so now I've changed careers and I'm teaching. I teach statistics, and I've taught it a couple of times, and I know it better than I know trig. I'm having to go back and refresh myself on trig as we go along. I did make an A on it when I took it, but that was 40 years ago, and I've used a little bit of it in my job over the time. But I appreciate your patience and bearing with me this semester. It's a learning curve for me also, and I know this virus thing has really added stress to everyone. With having to change the way that we do everything. And so I apologize if I haven't always got back with you as soon as you would have liked. Let's see, I've got Alex. I just now saw Alex trying to get in. I don't know how long he's been trying to get in. Hello, Alex. How long you been waiting? Well, Alexis, I don't have anything else. I'll hang on here in case Alex has got questions. So have a great day.
Another pair of shoes.
So can you hear me, Alex?
$50 on that. That's like $270. What is wrong with you, Cat?
Hello, Alex. Can you hear me?
Oh, yeah, man.
Testing, testing. Can you hear me, Alex? Hello, hello. I don't see anything back from you, Alex. Let me go find my phone. I'll be right back. Alex, can you hear me?
Oh.
Hello? Okay, how long were you waiting, Alex? I think I had this chat window up and your login was underneath it, so I didn't see it there. Were you able to hear this lecture? Okay. I've recorded it. I'm going to post this on Blackboard, this recording, so you'll be able to go to the video and replay this. the whole thing. There were no new assignments today, okay? I had talked about inverse trig functions the other day, and I wasn't happy with the quality of that discussion on my part. So I kind of redid it today, and I talked a little bit more about what's going on with these inverse trig functions and how to think about them and what kind of notation is involved. And that was the talk today. The final, if you've done all the homework since the midterm and you're happy with your midterm grade and your homework grade, then the final will be optional. However, if you haven't done all the homework since the midterm, then the final is mandatory. But whether it's optional or mandatory, when you take the final, if you score better on the final than you scored on the midterm, I will replace your midterm grade with the grade you get on the final. So it'll count for quite a bit if you end up taking it. I'm going to try to get everybody their grades Sunday evening so you know what you've got so far, and then that'll help you to decide if you need to take the final or not, okay? So if you got any questions right now, again, I'll get off here and I'll get this uploaded. This whole discussion I had today, I'll get it uploaded to Blackboard and you'll be able to view it there. And do you have any questions for me right now, Alex? Okay. Well, have a great weekend, and I'll probably, it's Sunday. Well, actually, later today or early tomorrow morning, I'll post a study guide for the final also, what you should be looking at if you're going to take the final. So thanks, and have a great weekend. Call me if you need something or email me.